Welcome, everyone. Let's get started on an essential topic for modern solution architects, defining the critical rules and constraints when building AI components using Copilot Studio, Microsoft Foundry, and Foundry tools. Welcome to our first slide, introducing the concept of AI solution rules and constraints. What exactly are we talking about? We are defining the operational, behavioral, and security boundaries that dictate how AI components function in your enterprise. The basics are quite straightforward. These rules dictate exactly how an agent behaves, what specific data it is allowed to access, and how it integrates with your existing business systems. Why is this our main focus in an overall AI strategy? Because without these strict rules, AI can become unpredictable. Establishing these constraints ensures that your AI solutions remain reliable, secure, highly compliant, scalable, and entirely predictable across all enterprise environments. How do we achieve this? Solution architects must actively define required guardrails for data movement, action execution, tool access, and responsible AI behavior from day one. For our deep dive, it's vital to recognize that architects cannot treat platforms in silos. They must create a unified rule framework that spans both low-code and pro-code platforms to prevent any governance gaps. Let's walk through the flowchart on your screen, which illustrates the foundational process of establishing AI constraints. At the top, everything begins with our business requirements. From this single point of truth, the architecture branches into three critical pillars of constraint definition. First, we branch into define data rules, where we set the boundaries for data access and privacy. Simultaneously, we branch into define action rules, determining exactly what tools and workflows the AI is permitted to trigger. Finally, the third branch is define network rules, which dictates the environmental and connectivity constraints. As you can see, all three of these pillars flow downwards and converge into one ultimate goal, a secure AI solution. By mapping your business needs through these specific rule sets, you guarantee that the final AI deployment is tightly governed, highly predictable, and perfectly aligned with your enterprise security standards. Moving to slide 2, we explore architectural foundations and platform roles. What does this entail? It's about recognizing how platform differences directly influence your architectural constraints. The basics are that Copilot Studio provides a low-code environment ideal for task and retrieval agents, while Microsoft Foundry is designed for pro-code, high-complexity AI applications and multi-agent systems. Why do we need to differentiate them? Because you must apply the correct constraints based on the specific risk level and operational overhead of each platform. How do we make this decision? The rule of thumb is to use Copilot Studio for workflow-bounded, task-driven scenarios, and reserve Microsoft Foundry for complex reasoning, multi-step orchestration, and custom tool integration. Taking a deep dive, we see that Microsoft Foundry requires developers to implement explicit governance for tools, models, and memory, whereas Copilot Studio imposes constraints natively through managed connectors and built-in safety filters. Take a look at the diagram displaying the divergence in our platform strategies. Starting on the left with platform choice, we see a split into two distinct pathways. The top path leads to Copilot Studio, which subsequently maps to a low-code/managed environment. Because it is highly managed, it naturally terminates at built-in safety, meaning the platform itself handles many of the baseline constraints. Conversely, the bottom path takes us to Microsoft Foundry. This maps directly to a pro-code/custom architecture. Because of the vast flexibility and power of this environment, it requires explicit governance. This visual perfectly encapsulates why your solution rules must adapt based on the platform. One relies on structural guardrails, while the other demands custom, architect-led governance to ensure safety and compliance. On slide 3, we focus entirely on constraints in Copilot Studio. What are these? They are the specific guardrails applied within this low-code environment. The basics of Copilot Studio constraints involve shaping agent behavior primarily through structured instructions and strict tool permissions. Why is this necessary? Copilot Studio is designed to provide a governed, safe environment for business users. Constraints are needed to prevent these agents from executing high-impact, unverified actions. How do we configure this? You must apply strict connector scoping to tightly control data exposure, ensuring the agent only accesses what it needs, while relying on the platform's built-in safety filters to restrict unsafe outputs. For a deep dive, it is the solution architect's responsibility to define rigid task boundaries. Even with built-in safety, you must construct the logic to prevent the agent from autonomously making high-impact business decisions, ensuring prompt instructions always reflect your organizational policies. Let's examine the flowchart representing the Copilot Studio constraint model. At the top, we have the Copilot Studio agent. Its behavior is immediately routed through two primary defensive layers. First, it passes through structured instructions, which guide its logic into a connector scoping decision gate. If the data or action request is within the defined scope, it proceeds to the allowed path, resulting in a safe output. If it attempts to reach outside its bounds, it is diverted to the denied path, resulting in a blocked action. Simultaneously, the agent is continuously monitored by built-in safety filters, an independent layer that also points directly to safe output. This diagram clearly demonstrates how Copilot Studio uses a combination of architect-defined scoping and platform-native filters to ensure every action remains secure and within policy. Slide 4 tackles constraints in Microsoft Foundry. What does this mean? We are talking about governance for pro-code, highly complex AI applications, and multi-agent systems. The basics here shift significantly from Copilot Studio. In Foundry, developers are entirely responsible for explicitly managing memory lifetime, conversational context, and data sensitivity. Why is the burden higher here? Because Foundry supports custom, tool-driven architectures and advanced generative behavior, which dramatically increases the risk of uncontrolled system modifications if left unchecked. How do architects manage this? You must apply rigorous evaluation pipelines to continuously audit safety, correctness, and model drift, while defining strict action boundaries for any tools that modify enterprise systems. For our deep dive, a critical strategy in Foundry is role separation. You must ensure that each individual agent in a multi-agent system operates with highly scoped permissions, limiting the blast radius if one agent misinterprets a prompt. This diagram illustrates the architectural constraints required within Microsoft Foundry. We start at the top with the Foundry application, which cascades into multi-agent orchestration. Notice how the orchestration branches into Agent 1 and Agent 2. Crucially, both of these nodes are explicitly labeled with scoped role. This visualizes the principle of least privilege in a multi-agent setup. Neither agent has full access to the system. From there, the outputs of both agents are channeled into an evaluation pipeline. This represents the mandatory auditing layer where safety, drift, and correctness are verified before anything reaches the final user. Only after passing through this pipeline do we achieve an audited and safe output. This flow highlights how proactive, architect-led governance replaces the built-in safety nets of low-code platforms. On Slide 5, we dive into managing Foundry tools. What are these tools? They encompass model catalogs, tool APIs, agent orchestration frameworks, and developer SDKs that provide a versatile foundation for agents. The basics of managing them recognize that because these agents can dynamically call external tools, precise permissioning is absolutely critical. Why do we focus so heavily on tool constraints? As orchestration complexity increases with multi-agent designs, the risk of misuse scales. These tools require carefully defined rules to prevent unintended consequences. How do you secure them? You must implement the principle of least privilege for every single tool and proactively use evaluation utilities to test failure cases and undesirable behaviors before deployment. Digging deeper, it is paramount that you define clear escalation rules. You must programmatically dictate the exact conditions under which an agent must stop and defer to a human operator, documenting all tool integrations with stringent security auditing. Let's trace the tool invocation process in this flowchart. On the far left, we have the Agent Requests tool, event. Instantly, this hits the least privilege check decision gateway. If the agent lacks the necessary permissions, the request follows the unauthorized path to a block request, termination. If authorized, the system moves to Execute Tool API. But the constraints don't stop there. Post-execution, we introduce another decision gate, confidence high. If the AI's confidence in the result is high and safe, it follows the yes path to return result. However, if the reasoning is ambiguous or low confidence, it follows the no path, triggering an escalate to human protocol. This diagram beautifully captures the dual-layer protection required for Foundry tools, strict access control on the front end, and behavioral escalation on the back end. Let's move on to data constraints and governance boundaries. When building AI components, what exactly are data constraints? They are explicit guardrails designed to prevent the overexposure of data and reduce the risk of unintended or incorrect information being generated. The basics revolve around providing agents with only the data they absolutely require. You must dynamically mask sensitive fields if the full data profile isn't necessary for the task. Why is this so critical? Without these boundaries, an agent might inadvertently access and leak cross-domain data such as mixing HR and finance records, which can violate strict regulatory obligations. How do we implement this? You strictly limit your grounding sources to curated, authoritative datasets, and you clearly define your memory policies, deciding whether agent context should be ephemeral or persistent. In our deep dive, for high-risk tasks like financial approvals or legal drafting, you must implement mandatory auditing for tool invocation and enforce human-in-the-loop checkpoints. Take a look at the flowchart on your screen, which visualizes how data access rules operate in practice. At the top, we start with the agent query. Before the agent retrieves any enterprise information, the query hits the data access rules decision engine. If the query requires standard operational data, it routes through the standard path to authoritative datasets, ensuring high-quality grounding. If the data involves PI or confidential details, it routes through the sensitive path, triggering the masked fields protocol to protect privacy. Finally, if the agent attempts a high-risk action, the system forces the workflow into a human-in-the-loop node, ensuring expert validation. All of these pathways converge at the grounded output. This diagram highlights how robust data boundaries prevent overexposure while maintaining the agent's contextual effectiveness. Slide 7 covers behavioral rules and responsible AI, or RAI. What does this mean? It means explicitly defining what an agent is allowed to do, and just as importantly, what it is not allowed to do. The basics involve creating behavior envelopes. For example, you program constraints that dictate agent may summarize data, but strictly mandate agent may not execute financial transactions. Why do we do this? To enforce your organization's security, privacy, and safety policies, using structured instructions to prevent the model from unsafe improvisation. How is this achieved? You mandate the use of bias and safety evaluation pipelines during development, and apply strict instructions for citing sources and avoiding incorrect information. For a deep dive into responsible AI, you must integrate mandatory human-in-the-loop checkpoints for any high-impact actions, guaranteeing that AI decisions are always overseen by accountable personnel. This diagram maps the flow of behavioral rules and responsible AI enforcement. Starting on the left, the system prompt feeds into the behavior envelope, which contains all your configured rules. When an action request occurs, it hits a decision gate. If the request fits an allowed behavior, such as summarize, it flows up to execute action. If the request is a disallowed behavior, such as decide or transact, it flows down to block action, stopping the process immediately. Even after an allowed action is executed, it doesn't go straight to the user. It must pass through the RAI safety pipeline, where bias and safety checks occur. Finally, it results in the final response. This visual proves that behavioral constraints are active at every stage of the generation process. Our final slide brings everything together under the unified rule framework and environments. What is this? It is the overarching strategy for defining deployment, networking, and operational constraints across all your AI platforms. The basics are that Copilot Studio operates securely inside the Microsoft 365 boundary and is isolated per environment, while Microsoft Foundry requires architected deployments like VNets and private endpoints for confidential workloads. Why is a unified approach necessary? Because a unified framework ensures consistent governance and security posture, regardless of whether a business user or a pro-code developer built the agent. How do we unify them? You restrict external tool calls to allowed domains, require API isolation, and establish strict service level objectives, or SLOs, for reliability and rollback procedures. In our final deep dive, solution architects must define a single, comprehensive set of rules centrally and then cleverly apply them differently depending on whether the application resides in Copilot Studio or Foundry. Let's review our final diagram, illustrating the unified rule framework. At the apex sits the unified rule framework, representing the single set of enterprise policies you've defined. This framework pushes down into two different deployment realities, Copilot Studio and Microsoft Foundry. On the Copilot Studio side, the rules are translated into tenant boundary isolation and rely on platform-enforced governance. On the Foundry side, the exact same rules dictate the use of VNet and private endpoints and rely heavily on architect-led governance. Despite the vastly different technological implementations on the left and the right, both pathways converge flawlessly at the bottom into unified enterprise compliance. This visually reinforces the architect's ultimate goal: diverse platforms, different mechanisms, but one consistent standard of security and governance.